Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is our third SPICE tutorial. And in this tutorial, we're going to look at the transient analysis of a circuit. And specifically, we're going to look at SPICE simulations of the step response of an RC circuit and the source-free response of an RC circuit. And so the first, I'll just start up SPICE here. The first netlist that we're going to look at is linked with the fourth lecture module where we look at the step response of a circuit. And here we just have a voltage source and a resistor in series with a capacitor. So I'm not going to bother showing you a diagram. You should be able to figure out the circuit just from looking at the netlist. But what's different is our voltage source is now using the pulse capability in SPICE. And basically what we need to do is simulate this act of flipping the switch and going from a 0 volts across our circuit to, in this case, 5 volts across our circuit. And we do that by putting the pulse command after the definition for our source. And so our voltage source is connected from nodes 1 to 0. And then it's going to generate a pulse. And the pulse is going to, just to sort of walk through what these numbers mean, the pulse is going to start at 0 volts. It's then going to go to 5 volts. It's going to do this after a delay of 1 millisecond. The rise time of the pulse is going to be 1 nanosecond. The fall time of the pulse is going to be 1 nanosecond. SPICE usually complains if you have 0 for these values, so I just chose something small. The length of time that the pulse is going to stay at 5 volts is 1 second. And then the period of the pulse waveform is 2 seconds. So that means after 2 seconds, so it goes to 5 volts, it stays there for 1 second, then it drops, and then after another 1 second for a total period of 2 seconds, it repeats, and then it goes back up to 5 volts again. So that's how we simulate sort of our switching on action in our circuit. Now, in order to look at how voltage in our circuit changes as a function of time, we have to do a transient analysis. So this is a little bit different. We're not doing an operating point anymore. The operating point analysis is for finding constant sort of DC voltage levels in the circuit. This is to examine how voltages change as a function of time. And so we want to perform a transient analysis for a total duration of 10 milliseconds using a step size of 1 microsecond. This step size is somewhat arbitrary. If you choose one that's too big, your waveform looks really chunky. And if you choose something that's too small, then your simulation just takes a super long time. And finally, once our transient analysis is finished, we want to plot the voltage across the capacitor as a function of time, and that's the voltage at node 2. And so when we run this simulation, this is what we get. So our plot shows a similar waveform to what we've seen with our theoretical analysis. At 1 millisecond, we throw our switch, and then we have this exponential increase up to the steady state final value of our capacitor voltage, which is equal to 5 volts, which is the value of our source. And that's consistent with the theory that we've been working through in the lecture modules. The netlist for simulating the source-free response, where we have a charged up capacitor and then we let it discharge through a resistor connected to ground, is simulated using this netlist. And in this case, there was actually a couple of ways I could have done this simulation. The first way was actually using the exact same netlist that we had for the step response, because you'll remember our pulse waveform, it went high for 1 second and then it went back down to 0 after that. And so if we could sort of zoom in on that point right after we switched our voltage source back to 0 again, we would see the exponential decay of the voltage across the capacitor. So that would have been one way to do it. I decided to use a slightly different approach in this netlist just to show you a bit of variety. So here I actually only define 2 components, the resistor and the capacitor, connected in parallel, both connected to ground. And then I use something called an initial conditions command to tell the simulation that when the simulation first starts, I want the voltage at node 1 to be equal to 5 volts. I then perform the exact same transient analysis that I did with the step response netlist. And in this case, I plot the voltage across the capacitor versus time. This time it's the voltage at node 1 rather than at node 2. And I'll just go into my other directory. And here when we plot that response, we can see the exponential decay down to 0 that our theory predicted, or the theory that we went through in our lecture module predicted.